All right, last week when we left, we talked about Aldol reactions, where if you have an aldehyde and catalytic base like sodium hydroxide, you can actually couple two aldehydes together to make a beta hydroxyaldehyde. And the mechanism is pretty straightforward. You form your enolate. The enolate can react with unreacted starting material. You have a proton transfer, and then you get your beta hydroxyaldehyde. Like I said, this reaction can go forward or backwards. It's an equilibrium. And it's really only favorable in the addition direction with aldehydes, not very favorable with ketones. And I showed you some tricks for predicting products, specifically identifying your alpha-beta bonds. And I really like color coding these. It's a good way to keep track of which reagent belonged to which starting material. And that comes into play later on too. So we did a few practice problems. And then we talked about aldol condensation, where if you heat your addition product, you can actually form an alpha-beta unsaturated aldehyde. And the big thing was this step down here, where if you have base around and you apply heat, you can kick off hydroxide as a leaving group and get that E2 type reaction to occur. It's only favored at high temperature, and that's primarily due to entropy and increased stability through conjugation. All right. We left off talking about this problem with crossed aldol reactions, where if you have two different types of aldehydes in solution, you can get 4 different products. So in the top example, we had 2 of the red aldehydes coupled together. Second one, we had 2 of the blue aldehydes coupled together. Then the third one, we had red and blue, where the red one was the enolate. And then the bottom one was where the blue aldehyde was the enolate and attacked into the red aldehyde. So then the question is, how can we avoid this complex mixture of addition products? And there's a few tricks that chemists use, so I'll show you the standard protocol. So tricks for avoiding multiple products. The first one is simply avoid the problem. I know it's a little passive-aggressive, but just don't mix different types. And then figure out how to make your product later on. That's one simple trick that occasionally students do. It makes life easy. All right, the second one is more common for chemists that absolutely need to make one. What they do is they drip the aldehyde or ketone into LDA. Does anybody remember what LDA is? Yeah, it's lithium diisopropyl amide. This is a really strong base. And by doing this, you form 100% enolate. Then, after you've formed 100% of your enolate, you would transfer to your second aldehyde or ketone. By doing this, your second aldehyde or ketone really doesn't have a chance to form an enolate very readily because there's no base around at that point, right? So that's one thing you can do. The key takeaway with this type of trickery is order of addition matters. So whichever one you want to be your enolate needs to go into the LDA, not the other way around, and you can't just mix everything up in one pot. Then the third one is kind of another clever trick, and that is use reagents where only one of them has alpha protons. So all of these can be done. The second one's typically what most chemists will do when they're trying to exclusively get one crossed aldol product. All right, so what we're going to do is we're going to practice a little bit. And for this practice problem, it's going to be a beta hydroxy ketone rather than a beta hydroxy aldehyde. And the question is, which starting materials would you need to make this? And you can use those same tricks that I showed you last week. So if you remember last week, the key thing we needed to do was to identify the alpha-beta positions. So the alpha position is always going to be the position next door to your ketone or aldehyde. It's right here. Beta is going to be one further away, and that's where the hydroxy group's coming off of. That means that this bond was made. And if we think about it, what did this bond used to be right here? Between the beta carbon and the oxygen. It used to be a double bond. Okay, so if we work backwards, we can say, all right, in order to make this beta hydroxy ketone, we must have had one half that looked like this, right? That's that left-hand side. And then on the right-hand side, we must have had an aldehyde that looked like this. And which one was going to act as the enolate, the left one or the right one? Looks like the left one must have been our enolate. So what you can do is, let's draw the overall scheme, or plan of attack, I should say. You start out with the thing you want to be your enolate. React that with LDA as step 1. So we'd say LDA, step 1. Step 2, we're going to transfer that to our aldehyde, which we know is the other component. And then step 3, we just need a proton source, so I'll say water. And by doing that, you can make your final product, which, like I said before, is going to be your beta hydroxy ketone. Does that make sense? Yeah. So up here we first identified which two starting materials we needed to make that product, right? And then we identified which of those two starting materials needed to be the enolate. And the easiest way to tell is this one didn't lose its double bond there, right? So it wasn't attacked into, it was the thing doing the attacking. That means we need to form an enolate out of that thing circled in blue. So in step 1, in order to form an enolate from that, we added it to LDA. And then after we added it to LDA, we added that aldehyde to it. And then after that, we quenched with water to ensure that everything was neutral. So you can work through these a little slower by breaking it apart and then going from there. Yep.
Can you slow up a little bit? It says used to be double bond. How do you really know that? Because I kind of feel like I'm getting this, but it may be something that,
so your question was, how do you know that that used to be a double bond? A lot of it's just pattern recognition. So if you go through the reaction mechanism, right? In all of these reactions, you've got an enolate attacking into an aldehyde or ketone, resulting in loss of a double bond in the thing that was being attacked.
What you say, aldehyde or ketone?
Yeah, it can be either. Typically with aldol additions, it's going to be aldehydes, but you can force it to attack in to ketones under some circumstances. Yeah. All right, let's do another one. We're going to do another synthetic route. And for this one, we're going to add a new twist to it. This time we're going to have an alpha-beta unsaturated aldehyde. So devise a synthetic route. I'll give you a minute to work on this, but check with your neighbor and see if you agree. Yeah, right next door. So that's a good point. So let's identify our alpha and beta carbons here. I'm going to zoom in. Alpha is going to be that carbon because it's right next door to the carbonyl carbon on the aldehyde. Beta is going to be one further away, so we've got a beta carbon right here, but that one doesn't really matter that much. Typically, you want your beta carbon to be functionalized, so this one has an alkene on it. That's the more important one. So when we look at this, the bond that was formed must have been between that alpha-beta position, right? So now what we can do is work backwards and say, all right, what two pieces did this used to be? So just like before, we can break this apart. The one on the right is really easy. We know that this one must have been our enolate because its double bond between its carbon and oxygen was untouched. And now the question is, what was the thing on the left? What did it used to be? So what's the missing half?
Maybe a phenol and a benzaldehyde.
Benzaldehyde, exactly. So if we look at this, the thing on the left must have been benzaldehyde, right? Where did the OH go that used to be on the beta position? We eliminated it off, right? So if you remember, under certain temperatures, we're going to go back up in our notes. Keep on going, keep on going. Under certain temperatures, specifically the thing highlighted in yellow, you can actually eject off that hydroxide and form an alkene between the alpha-beta positions. So this must have been run under high temperatures, which is also another important clue. Okay, so we know it was high temperatures. We know that we've got these two important pieces. Now the question is, does order of addition matter?
No.
Why not? Yeah. Only this reagent has alpha protons. Right? If we look at it, this carbon's alpha, that has protons. If we look at benzaldehyde, it does have an alpha carbon, but there are no protons coming off of it. Therefore, you can't form an enolate from benzaldehyde. Okay, that makes our lives a heck of a lot easier. We don't have to do that whole LDA nonsense where we add things in a specific order. Instead, what one of my students referred to this as is a shake and bake. You just combine them with sodium hydroxide and heat the snot out of them. By doing that, we're able to get the condensation product. It looks like this. You don't need LDA. Does that make sense? So like I said, it doesn't matter if you're mixing two identical products, you don't have to worry about LDA, or if you're mixing a product or reagents where only one of them has alpha protons, you don't need LDA. But if you're in that situation where both of them have alpha protons, that's when order of addition matters a lot. Make sense? Okay, we gotta jump into a new reaction, but the new reaction is very similar to aldol chemistry. Very, very similar reactivity. This is called a Claisen condensation. And it's basically the analogous reaction with esters. So let's take a look at this. And I like this reaction a lot because it's very intuitive with the mechanism. So for example, I've got an ethyl ester here. And in the first step, you treat it with a strong alkoxide base. And one thing I will say, and I'll reiterate this a lot, is this alkoxide base, the ethoxy, needs to be the same as the ester type, right? So if you've got an ethyl ester, you need to use ethoxide. If you've got a methyl ester, you need to use methoxide. And then in step 2, you treat it with water or acid. I'm actually going to change this to acid just to be consistent. And you can couple 2 of these together. And if you remember, this is our alpha position. This is beta. This is a beta keto ester, meaning you've got a ketone on a beta position right near an ester functional group. Does that make sense? Let's just make a note down here. Your alkoxide base should be the same as your ester. What do you think it would happen, for example, if we were to use methoxide here instead of ethoxide? We might be able to swap out that ethyl ester for methyl ester. So if you remember back to the chapter where we talked about transesterification, you don't want to accidentally mix things up. You want to keep it in ethyl ester, so you got to be consistent there. All right, let's try to figure out what the mechanism is. And I'm actually going to give you a few minutes to look at this mechanism by yourself, and I want you to check with the neighbor and see if you're predicting the mechanism correctly. All right, let's try this as a class now. So what do you think the first step is going to be if you've got a strong base? Deprotonate, right? We saw this over and over again with the aldol, where it's going to grab one of these alpha protons. We get our resonance stabilized conjugate base. I'm not going to show the remaining protons. And then it's important to remember that ethoxide's not a really good base. It's not as good as LDA, so we're not going to be forming very much of this under equilibrium conditions. So you're still going to have a lot of this ester floating around. And I'm just going to write unenolized starting material down here. Okay, if there's unenolized starting material, just like with the aldol, your enolate that you did form can quickly attack into your unenolized starting material and kick up electrons. And now when you've done this part, you've got an oxygen with a negative charge, got an ethoxy group, and what do you think the last step is going to be?
Attack by itself.
Yeah, you've got a leaving group here. You can clamp down, kick off your ester, just like we saw previously in the last chapter. And you kick off ethoxide in the end. So this would be your final product for that. The problem with this, though, is we've regenerated base. We have alpha protons still, and these are unusually acidic. Why are they unusually acidic? They're in between 2 carbonyls, exactly. So before you can ever isolate your product, what ends up happening is this will really quickly pull off these acidic alpha protons. Unavoidable. The acid-base chemistry happens so fast, you can never stop. And then in your last step, you need to ensure that you've got weak acid around. It can't be very strong acid, so that this can steal its proton back and leave you with your final product. Whoops. And there you go. Does that make sense? So this is your beta keto ester that we were talking about. You've got a ketone in the beta position next to an ester. All right. So if you notice, just like with aldols, this one used two identical starting materials, but we could theoretically mix it up and mix two different reagents together. And that's referred to as a cross Claisen. So that's where we're going to start next. And the rules are very similar. And with the cross Claisen, it's typically done this way, where you have one ester plus one enolizable ketone or ester. Enolizable, if I can spell that. Really could be any one of those three. So I'll show you an example of this. The first one, we've got an ester. And I want you to help me name this ester. What would this be called? Not everybody all at once. A lot of you made this in your synthesis project. Oh boy. So remember, you always list the functional group coming off the oxygen, so it starts with methyl, and then it would be benzoate. So this would just be methyl benzoate. So this would be your ester. A what? No, you only put an N for things coming off of nitrogens. Yeah. So this is going to be your ester, so that's filling in this 1/2, right? So we've got that 1/2. Now we need our enolizable functional group. So in this case, I'm just going to pick acetone. All right, and what base should I use for this reaction? Yeah, enolizable ketone. And just like before, we need to pick a base that corresponds to our ester leaving group. So this one would be sodium methoxide, followed by an acidic workup. And now we need to predict what our product would be for this cross Claisen. Yeah, so in this case, I said this one's an enolizable ketone. Why is this one not enolizable? No alpha protons, right? Which means this one over here, you've got to pluck off one of those alpha protons, form an enolate. And that means once you form this, for example, let's say you form an enolate right here, then this can attack in, kick up the oxygen, and then this eventually is going to be lost as a leaving group. So really quickly on scratch paper, you can work through these. The key is trusting your arrow pushing. I know it seemed like for the first term or two that I was being super nitpicky with arrows, and this is why. I want to make sure that you, by the end of the year, can trust all of your arrow pushing. So let's take a look at the final answer for this one. And like I said, if you form an enolate, the enolate would first attack in like this, kick up electrons, and I'm going to cheat and just condense this into one step. After that, it's going to clamp down and kick off methoxide as a leaving group. So just really, really quickly, I know this isn't going through the tetrahedral intermediate. We know that our product for this one must still have that double bond there, and we must have coupled it onto the other ketone, which is highlighted in green, right? So this bond right here is your new alpha beta bond. Or sorry, your new bond. It's not alpha beta this time. Does that make sense? So you can quickly do some of these as long as you trust your arrow pushing. I'm just going to erase this just so we're making our notes clear. Does that make sense? So in this example, we only had one starting material that had alpha protons. Just like with aldols, you might run into situations where both of them have alpha protons. And the same trick applies, but let's reiterate it. So if both starting materials have alpha protons, first add the one you want to enolize to LDA. Then add your second starting material. And just like before, the then part, meaning order of addition, matters a lot for these. You can't just mix everything together with LDA or else you'll get 4 different products out. Make sense? All right, so now I've got a good challenge problem. For this challenge problem, I'll give you a hint. But the starting material looks like this. For step 1, you'll add this with sodium ethoxide. Step 2 is going to be acid. And the hint is you're going to form a ring system. So see if you can work through this mechanism and figure out what ring you're forming by using basic arrow pushing techniques. All right, just for the sake of time, I want to get started with this one. So let's take a look at the first step. What do you think the first step's going to be? Deprotonate an alpha proton. Sounding a little redundant at this point, but first step is going to be that. We're going to form our enolate. Doesn't matter which side you pick because it's symmetric, right? So I could have picked the ones off the left-hand side. Doesn't matter. All right, now that we've formed our enolate, we could attack into leftover starting material. However, entropically, that's not as favorable as attacking itself, right? So in the next step, this can actually just reach in and attack itself and kick up electrons. But what I really like to do whenever I do these is number carbons. Otherwise, it's very easy to get lost. So for example, carbon that attacked, I'll number that carbon 1. Then there's carbon 2, carbon 3, carbon 4, and then carbon 5 over here. So we are forming a 5-membered ring. So I'm just going to go ahead and draw my 5-membered ring. And then inside, I'm going to go 1, 2, 3, 4, 5. Carbon 1, we know we have this entire group dangling off of it, so I'm going to fill that in. Carbon 2, nothing coming off of it. Same with 3, same with 4. Then we go over to 5. 5 has an oxygen with the negative charge coming off of it now. And then this ethoxy group. So that looks good to me. What's the next step going to be? Yep.
Sorry, but why not have the lone pairs attack to the right side of the
So you're talking about attacking there? That would be impossible. Geometrically, it can't attack a carbon right next to it like that. It has to have flexibility to attack a carbon.
And why not have number 6 in the oxygen?
I mean, you can. What I was trying to do is identify the correct ring size. You can number it however you want. The key is keeping track of carbons here. Yep. Or just atoms in general. So now we've got this good leaving group, or decent leaving group, I should say. So we can clamp down, kick this off. We still have all of these functional groups. We've regenerated our double bond. We've got ethoxide, but we did have that problem where we've got this alpha proton in between both carbonyls that will quickly get deprotonated. which is why we need acid in that last step. And the acid will give its proton to that enolate in order to give you your neutral product. And there you go. This is called an intramolecular Claisen. Oops, that should be an R. And this also goes by a different name, depending on who you're talking to. This is commonly referred to as a Dieckmann cyclization. I think there's two N's. Oh. If only it were that easy to get a reaction named after yourself today. Just take one and make it into a ring. So it's a pretty simple reaction, but what makes it unique is you're forming a ring system and it's just an intramolecular enolate attack. Make sense? All right, I've got a few tricks and hints for you. So the first one is Claisen is good for dicarbonyls. And I'll show you what I mean by that. A dicarbonyl is when you have two carbonyls separated by a CH2 bond. So if you see this product somewhere in there, good chance you can make that with a Claisen reaction, right? Because all of our Claisen reactions ended up with two carbonyls right next door to one another. So Claisen condensations are good for that. Aldol is good for beta hydroxy or alpha beta unsaturated carbonyls. And I'll show you what I mean by that. So the top one, beta hydroxy, is another way of saying you've got one carbonyl here, and then you've got a hydroxy group coming off this position. So that would be beta hydroxy. You can make that really easily with an aldol. Is that done at high or low temperatures? Low temperatures, right? And then the last one says, all right, you can do an alpha beta unsaturated reaction. Looks like this. I'm just going to do red squiggly lines to indicate it's coming off something else. And that's done under high temperatures. But both of these are aldol reactions. The dicarbonyls are typically Claisen reactions. That is a good hint for your pod. The pod that I gave out last Thursday, we didn't get far enough, so it'll be due tomorrow. But see if you can figure out a good strategy for making that product starting from acetophenone. Acetophenone is your carbon building block for that reaction. All right, I'll see some of you in lab.